Okay, I'm going to take you through a simple problem. We've got a framework, simple square like that. It's got 3 meters in this, well, it's not quite a square, it's a rectangle. 3 meters this direction, 4 meters across. It's labelled up as, here we have a hinge, and we've got a pivot here. Going to apply 6 newtons here and 12 newtons here. Okay. This is going to be A, B, C and D. Okay. Now, what would be really useful if you're doing this problem would be to pause the video, because we're going to take it in stages. Skip over the first stage, and see if you can work out the next stage that we're going to go on to do. So the next stage will be to work out what the reactions are. So find out what RAX is, and find out what RAY is, and find out what this reaction here is. So that's going to be RDY. So pause and see if you can work out those values. Well, hopefully you pause the video. You might have just cheated and carry on watching. It's fair enough. So I'm just going to give you the answers because we've already done problems like that. So I don't want to go over reactions again. And you should have got 16.5 newtons there. That's a hinge, so we get a negative reaction of 4.5. So I'll draw it as an arrow pointing away. And a negative, again I draw it as pointing away, 6 newtons going in that direction. And these are my applied values, 6 newtons going in that direction, 12 newtons going in that direction. And remember, this is A, B, C and D. Okay. So I want to find all the forces inside the members using method of joints. What do I do? So assuming that we're at this stage. So pause the video and tell me what you're going to do next. Okay. So, give you a bit of a hint. I'm going to do method of joints. Where am I going to do my method of joint? Am I going to do it at A, B, C, or D? What do you think? Have a think about it. There's 2 possible right answers. So the first one is that you're going to take method of joints at B. So we could take method of joints here. Or we could take method of joints at D. Why? Those are the 2 correct answers. Well, both of them will have 2 unknowns. Makes no difference which one I choose, so I'm going to choose method of joints at D. So the next thing I want to do is to make my cut through that joint and just take out those forces there. So I've got 16.5 being applied. I've got now this internal force which I've exposed, and that's going to be called AD. And then I've got this other force going up and exposing that and calling that CD. Okay. And so we're doing method of joints, and we're doing it at D. Where's the sensible direction to take our forces, resolve our forces? Well, in this case, the sensible one to start with would be, let's resolve forces in the x direction. Why the x direction? Because there's only one force, minus AD equals 0. Therefore, AD equals 0. Okay. Now let's resolve the forces in the y direction. So therefore I've got a force going upwards, 16.5, and another force, CD, going upwards. So therefore CD is going to be minus 16.5 newtons. Right, so good, fair enough. So let's now we've got two options really. So we worked out these values. We've worked out that AD is 0. So I've worked out here. I'm going to write it down here. AD equals 0. And I've worked out here CD equals minus 16.5. So I could actually go to joint A next. Why? Because I know that the internal force AD, I need to go to red. I know that this internal force here is actually 0, which means I've actually just got two unknowns. So that's one possible option. Or I could go back to my original plan and go for, oh dear, and go for go back to B. So I've now got options here. I could go back to the B, or I could go to A. Since I knew B it's nice and straightforward, everything's horizontal and vertical, I think B is the best one to choose to do next. So we'll go and we'll do method of joints at B now. Okay, so we've got BC going in that direction and AB going down in that direction. So you want to draw another diagram. So of that joint, we've got BC going off in this direction. We've got AB going down in this direction, and we've got this applied force of 6 newtons going there, and we're doing method of joints at B. Okay, which is the first one to choose? Well, it's probably, I should really choose summing up forces in the y direction. So therefore I have minus AB equals 0. Therefore I have AB equals 0. That's straightforward. Now let's sum up forces in the x direction. Okay, so therefore I'm going to now have BC plus 6 equals 0. So we're going to have that BC equals minus 6 newtons. It's in compression. Okay. So now let's do the last method of joints. So what we're going to choose now? Well, we could go back to method of joints using it at A, I suppose. Shall we do that? Or we could do it at C. Okay. Advantage of doing it at C is we've only got one external force being applied. Advantage doing it at A is I've got a 0 along the base. So I think I will do I'll do A. Be brave. Right, so we've got a force going off in this direction. That's my AB. Got a force going off in this direction. That's my AC. And then I've got a force going off in this direction, AD, which I happen to know is 0. And then we've got forces being applied of 4.5 newtons going downwards. And we've got a force going in this direction of 6 newtons. Right, now I know from the previous joint, from joint D, that AD equals 0, so I could put that on my diagram and then say what is a good direction to resolve forces in, and I would say it would seem that the good direction to resolve a force in would be the AC direction. The other thing is to draw a little geometry diagram, because I'm going to do some hardcore maths. So what do we have as the geometry? So we had free, vertical, free, vertical, 4 going along horizontal. Ah, that's a 3, 4, 5 triangle. So this angle here, theta, is going to be this angle here, theta. Let's resolve the forces in the x direction. And what we're going to get. So we're going to get that we get a minus 6 plus AD, which is 0, plus AC cos theta equals 0. So we're substituting that AD equals 0, and that gives us that AC cos theta equals 6. Cos theta, what's that? Well, we can do a little table here. So cos theta equals 4 over 5. Sin theta equals 3 over 5. Right, so done my geometry here. So it's good to do little kind of rough notes of your geometry over on the side. So cos theta should be 4 over 5. So AC equals 6 divided by cos theta, which will give me 6 divided by 4 times by 5. So that's what, 30 divided by 4, 15, 7.5. So 7.5, and it is going to be in tension. Okay, so now we could come back and we could label up our whole graph at the end. I think I've got all my forces now. Did I have AB? Have I found AB? Yeah, AB is 0. Right. So let's label everything up. So we have the external forces, .5, 6. The applied, we've got an applied load of 6 here, applied load of 12 here, and we've got another reaction here of 16.5. I'm calling this A, B, C and D, and now we can put numbers of what's happening to the bars in this framework. So I found here, for example, that AC is 7.5 newtons in tension. So that's 7.5 newtons in tension. Here at point B, I found that AB was 0 and BC was -6 in compression. So AB is 0. For that we can write undetermined or put a U. And BC was -6. So we've got -6 in compression. Okay. And at joint D I worked out that AD was 0 and CD was -16.5. So that's minus 16, and that's going to be in compression. And here we've got 0 undetermined. So in principle you can these 0 bars, I don't actually kind of need them really. There's the weight is pushing down here, and this bar here is then transferring weight from this joint and from this framework. So it's only really these 3 bars that are kind of essential for this framework. Wouldn't really want to remove them though. It would cause things could waggle around, you see, if I did that then. But does this make sense? So if I'm pushing down here, yeah, I expect a lot of compression in this bar. That sounds correct. If I'm pushing this side, well, that's going to kind of push around towards that pivot. Again, I expect that to be in compression. That makes sense. So what about the last one here? Well, in terms of the reactions, I can see these reactions are trying to pull this away. So they're trying to be pulled away. And I could also say, well, this bar here is trying to be pushed away in this direction. So we've got stuff being, and also being pushed in this direction. So we've got stuff being pushed vaguely off in this direction. Well, actually it's going to be more this direction. And we've got stuff being pulled in this direction. So we do have some forces which do all seem to be kind of going off in that direction. So it does seem to be that should be in tension. Okay. So that's my example.